Yeah, good morning, class. How are you? Today, we are going to treat atoms and molecules. Atoms and molecules. That is the topic for today. Atoms and molecules. Objective of the study, the objective of this topic is to enable the students to understand the basic concepts of atom. Secondly, for the student to also understand the concepts that are guiding the formation of molecules and how all these are related to real life. These are our objectives. To understand the basic concepts of an atom and the fundamental guiding rules that lead to the formation of molecules and how we relate these to real life. That is the thing. So we go now to what is an atom. As I told you last week, an atom is the smallest unit of anything. The smallest unit of anything or the smallest unit of life. The smallest unit of life. Atoms are the building blocks of matter. Atoms are the building blocks of matter. And what is matter? Anything you can touch, anything. For example, the paper. For example, this bowl right I'm using, that's matter. Our body is matter. The food we eat, matter. The clothes we wear, matter. And all these are made up of atoms. Atoms are the building blocks of all these particles. Now, the thing is, how can we say that atoms are the building blocks of matter? There was a scientist called John Dalton. He carried out an experiment on matter to understand how matter was made up of. He chopped up a small piece of substance into the smallest part, and he realized that that part was indivisible again. And he concluded that that part was an atom. Therefore, take for instance a cube of sugar. This is a cube of sugar. This is a cube of sugar. A cube of sugar can be divided into 4 pieces. This cube of sugar, if you divide it into 4 pieces, we take this section of it and redivide it again. And when we divide this, it goes to another piece, which is smaller again. When we divide it again, it goes to another smaller one. When we divide it again, it goes to the smallest, one of the smallest one. It gets to a substance that can no longer be divided. For instance, this one, and it got to a point that this cube of sugar can no longer be divided. A cube of sugar divided into 4 pieces. One of the pieces is used and is subdivided again into another piece. One of it is also used again to a smaller one again. Then the smaller one again is subdivided again, just continuously like that on, and it gets to a certain level to the smallest piece in a cube of sugar that you can no longer divide it. That one, Dalton called it an atom. An atom. This is the smallest one. And he said atoms are indivisible, according to his experiment. Atoms are indivisible and they cannot be destroyed. That is how he came about. Take for instance, this was a real structure of how he did it. He came, he divided the piece of substance, matter, that he was working on. He chopped it into smaller pieces, into another smaller one, where he got 3 pieces. Then he took a certain piece from that one that he chopped and further chopped it. Just like that, he divided it into the next piece. which made of two particles. Then from there he took again and subdivided it. And it went right to the level that it was indivisible again. And that was how Dalton said an atom is indivisible. Any substance that you get to a certain level that it can no longer be divided, Dalton termed it an atom. And these atoms are what we call the building blocks of matter. These atoms are they build up themselves into molecules. These atoms, they build up themselves into molecules, and will give us matter. That is why we are saying that atoms are the building blocks of matter. Atoms are the smallest particle of a substance that can take part in a chemical reaction. These are what we call atoms. Dalton again went further and said these atoms of a particular element are alike. They are the same. Atoms of a particular element are the same. For example, atoms of chlorine are the same in their physical property and also the same in their chemical property. Take for instance, atoms of metals. They are the same in their physical property and also in the chemical property. For example, let's say an example of the periodic table. Take for instance, this is the periodic table. This is a sample of the periodic table. This is a sample of a periodic table where we have group 1 elements, group 2, group 3, group 4. And these are metals. 1 and 2 are metals. This is it. 1 and 2 are metals. If we say group 2 element, we are talking of beryllium. Group 2 element, we are talking of beryllium. We are talking of magnesium. We are talking of calcium. 1 element, we are talking of hydrogen. We are talking of lithium. We are talking of sodium. We are talking of potassium. All these elements, all atoms of this element of group 1, they are similar in chemical property. They are similar in physical property. When they react, let me say with atoms of group 6 element, let me say oxygen, they will form oxides of group 1 elements. When they react with, these are group 2 elements. When they react with this same with oxygen, they will also form oxides of group 2 elements, oxides of metal. Now, that's why Dalton said atoms of a particular element are alike. They are the same in their physical property, and they are also the same in their physical property. Then, for instance, magnesium of group 2. This is magnesium. Magnesium is an example of a group 2 element. This is it. This is magnesium here. Magnesium, if it is reacting with oxygen of the group 6 element, take for example plus oxygen, what happens? They must form an oxide. And the oxide will be magnesium oxide. Now, is the equation balanced? No, the equation is not balanced. There are two atoms of oxygen here. Here, there's only one atom of oxygen. What do? We need to add a 2 here. We need to add a 2 here. We don't add a 2 here, but we add in front. We add in front to balance the equation. We don't balance it from here. We add here. Now we have 2 atoms of oxygen and 2 atoms of oxygen on this other side. The equation is balanced for oxygen atoms. Now for magnesium atoms, we have 2 atoms. We have 2 atoms of magnesium here, but it's only 1 here. And what do? We need to add 2 here to balance the number of atoms of hydrogen and of magnesium that are reacting. Therefore, we have 2 atoms of magnesium here reacting with the 2 atoms of with a molecule of oxygen to form an oxide of magnesium. Now, atoms of group 2 elements, when they react with oxygen, they will form an oxide of group 2 element. So that's why Dalton said atoms of a particular element have the same chemical properties. This is just an example. The same thing goes with the group 3 element. Take if it's an aluminium. An aluminium is reacting with oxygen here, is reacting with oxygen. The same reaction will be aluminium plus oxygen to give an aluminium oxide. So all metals, when they react, metals with the same group, when they react with oxygen, they form oxide of that metal. let's go back to the properties of an atom. Now, when Dalton said atoms are indivisible, atoms of the same element they have the same physical and chemical properties. Atoms cannot be destroyed. After a period of time, there was another scientist who came up with the idea of to know what the composition of an atom, and that was Ernest Rutherford. Ernest Rutherford carried out an experiment where he passed a beam of alpha particles, through a thin gold foil, and in noticing it, he realized this. He passed a beam of particles that were coming. These particles, there was a beam, there was a thin foil. All these particles passed here. Some parts went right. All these were going like that. Some of them went out. But at the nucleus of the foil, the nucleus was positively charged. Because these particles are positively charged, all alpha particles are positively charged. As these particles were positively charged, as they were passing, some that did not go close to the nucleus passed by like this one. They went all through. Then the one that went close to the nucleus, the one that went through to the close to the nucleus were deflected. The one that went to the nucleus were deflected. These were deflected. These particles were deflected. Now, Rutherford concluded that after passing a beam of alpha particles which were positively charged through a thin gold foil, he realized that some particles that did not go close to the nucleus were passing by, and that some of the particles were repelled and deflected from the center. Then there was an idea that came to him that something must have caused that these particles that are positively charged, something must have caused them to be deflected from the center, and that gave him the conclusion that there was another particle that was positive in this nucleus that must have caused the deflection of the positive alpha particles. And as you know, positive charges will always repel, but negative charges will come together. Therefore, that was the reason that he concluded that there must be something positive here that must have repelled the positively charged particles, and gave the conclusion that the nucleus was positively charged. Then the nucleus, after Rutherford concluded that, he now concluded that the nucleus has something in it that is positively charged, that is causing the deflection of these positively charged alpha particles, and that was the proton. He was not the one who brought the idea of proton and the neutron. So he presented it in this form. This was the right format where it was presented. This is a nice sketch, a sketch on how Rutherford presented it. These are the beam of alpha particles that Ernest Rutherford passed through a thin gold foil. These are the particles that were positively charged. These particles were positively charged as they were passing by. They got to the nucleus. Those that got to the nucleus were deflected because they were positively charged, and two charges, the nucleus that was positively charged, and they had to repel each other. So they were deflected. But those particles, those particles of the alpha particles that did not come close to the nucleus had to pass by. And that's the conclusion that the nucleus was positively charged and contained some subatomic particles which were positively charged. And that was the conclusion that the nucleus is made up of protons that are positively charged and also neutrons. Now, Rutherford went further and came out with a model on how atoms are arranged in an atomic structure, and came to the point atomic structure, how atoms are arranged in how the subatomic particles are arranged in an atom. He went further And that, take for instance, this is the nucleus of an atom. This is the nucleus of an atom. And that the atom has, from his experiment, that the atom has positively charged particles, which he called them the proton. The nucleus of the proton, which are positively charged. And other particles we call that are neutral in charge, and we call them the neutrons. And he also concluded that around the nucleus there was an orbit. There was an orbit we call the shell. That the electrons were revolving around it. So he said the electrons that were negatively charged were moving around the orbit. And he named this a shell. This was a shell. And he also named this the nucleus that contains the nucleus that contains the proton and the neutrons. This, from the nucleus, he concluded the nucleus is positively charged because of the proton and the neutron, which are negative, which have no charge. Now, these particles here are the ones that give the atom a stable structure. The protons that are positively charged are neutralized by the neutron. These protons that are positively charged make the nucleus to be positively charged. And outside the electrons, outside the proton, we call them the orbits. And these are arranged, the orbits are arranged depending on how the electrons are. They are arranged in shells. The first shell, the second shell, and the third shell. The first shell of the orbit is called, this orbit here, the first shell is called N. Is it K? Which we say K is N equals to 1. That's the first shell. Then the second shell, that electrons are also found there. Let's say these are electrons. The second shell, we call it L, which is N equals to the second shell, that is N equals to 2. The third shell, we call it M equals to 3. And the fourth shell, we call it N, which is equal to N equals to 4. The shells will continue, and this is how electrons are arranged. These electrons are arranged, this is how electrons are arranged from the first shell, which is K equals to 1, to the second shell, which is L equals to 2, to the next shell, which is M equals to 3, and to the fourth shell, which is N equals to 4. All these electrons are, on these shells, the electrons are arranged there. And the first shell, take for example, how the electrons are arranged in this shell. N, there is a formula, we say 2n squared, where n is equal to the number of shell, or the shell number. For instance, how many, this is the first shell, n equals to 1. This first shell, if n is equals to 1, how many electrons are supposed to be there? It will be 2. We have 1 here, 1 square. Therefore, 1 square is 1 times 2. 2 electrons are supposed to be in the first shell. The second shell, which is L, and which is n equals to 2, is supposed to be, if it's 2n square, which 2n square, which therefore, if we replace n by 2, then 2 square, then 2 square is 4. 4 times 2 is what? 8. There are now 8 electrons in the second shell. Just then the third shell like that. The third shell, that's how they are supposed to be arranged. We go to the level that at the last shell, we call it the valence shell. The valence shell that has electrons. We call it the valence shell because it is the outermost shell. The outermost shell from the nucleus is called the valence shell. And all electrons at the outermost shell, we call them valence electrons. These are electrons that are active and can take part in a chemical reaction. So now, after this arrangement, this is the nucleus. This is the nucleus. That's the nucleus. These are the shells, and these are the protons. That is how Rutherford came out with this idea on how electrons are. The subatomic particles are arranged in an atom. This goes to cancel the idea that the first scientist, John Dalton, said atoms are indivisible. That is, atoms cannot be divided again. But because of this experiment that Rutherford carried out, he saw that there were other particles in an atom. For example, the proton that was causing the deflection of other alpha particles. That is why he concluded that atoms, again, even though they are too small, can be divided again into subatomic particles. We call them the protons, the neutrons. And that is how they came about the structure. And if it is well represented, this is a structure. For example, a structure of an atomic structure. This is the nucleus of an atom. Take, for example, atom of helium. We said atoms of the same element are the same in every part, in the chemical property and physical property. But atoms of different elements are different in their sizes and in their physical property. Now, take for instance helium. This is a helium atom. How is it? How are the subatomic particles arranged in it? Just as I explained here. Now, helium of the periodic table has helium of the periodic table. This is a sample periodic table. Helium of the periodic table is a group 8. That is a noble gas. That is a noble gas, or what we call an inert gas. I call it an inert gas because it cannot react. It has a full atomos shell. So there are no valence electrons there that can take part in a chemical reaction. Therefore, we call it, they are all inert gases, or what we call noble gases. This is helium here. Helium has two. Yes, it has two. You're correct. Now these two has two protons. These two protons here has two protons. Now, this is how they are being represented here. This is a helium atom. It has two protons. It has two protons and two neutrons in the nucleus, with two electrons that are revolving around the orbit. So now, these two electrons, this is how they are well represented. This is a helium atom here. Now, in the helium atom, this is the nucleus. And in that nucleus, we said that from Rutherford experiment, the nucleus is positively charged because of protons. These are the two protons that are represented in the nucleus. Again, there are two protons there, and there are two neutrons there. These are the two neutrons that are in the nucleus of the helium atom. Now, this is the nucleus. Then this is the first shell of the nucleus, the first shell of the helium atom, with two electrons that are revolving on the orbit. So this is how they are represented. And these two electrons, we call them valence electrons in the helium atom. The same thing goes with the carbon atom. The same thing goes with the hydrogen atom. Hydrogen belongs to group 1 of the periodic table. It has one proton, an atomic number of 1. This is how it is represented in hydrogen. This is hydrogen. This is the nucleus. This nucleus here, and this is an atom of hydrogen. This is the nucleus. The nucleus has one proton, and it has one neutron, and only with one valence electron in the atomos shell. Now, that is a full representation of an atom. The same thing goes practically. Let me show you a good example. If this is an atom of, for example, these are two atoms. These are two atoms. The atom of helium or the atom of hydrogen. Or this is an atom of carbon or the atom of helium. These atoms, as you see it, take for instance, this is an atom of carbon. This is how it is represented. This atom has electrons. Let's say the dotted points are electrons that are around its orbit, or electrons that are in the atomos shell. These are the electrons that are presented on outside, that are revolving, going around the orbit or on the shell of this atom of carbon. In the nucleus of this atom, you will see, look at it. This atom. This is the nucleus. This is the nucleus, and this is the nucleus. And the nucleus, there are four protons there, and then there are 6 protons there if it's carbon. There are 6 protons there. There are 6 protons here if it is carbon, and there are also 6 neutrons in this nucleus. That is how an atom of an element is represented. Outside, on the outermost shell, we have the valence electrons. Inside the nucleus, we have the proton and the neutron that are located there. That is how an atom is. When this and atom come together, they come together and they want to react with another atom, they have to break the bonds between them and they rearrange them to come to what we call a molecule. That's good. The same thing goes with the atom of helium. It's the same thing. Atoms of the same element are different in chemical property, in sizes. That's why you may find these ones are red, are blue, and these ones are also black. These are different atoms of different elements that are different with different physical and chemical properties. That is a good sample of how atoms are arranged in particles are arranged in an atom. We call it the atomic structure of an element. Thank you very much. Now, to go further, in this case, these are valence electrons. These valence electrons, they take part in a chemical reaction. These electrons that are outside the nucleus like this, these are electrons that take part in chemical reaction. Why do we say they take part in a chemical reaction? Because they are not stable. One thing is that they are not stable, and to regain their stability, they are not either full. They need an electron to fill up, to bond with, to make up a stable form. Secondly, because of the distance from the nucleus. They can ask you, why do you think that only this electron, because there are electrons inside here, there are electrons inside here, and there are also electrons outside. Why is it that only these ones are reacting and these ones are not reacting? These ones they can easily react. They can easily bond to another compound and another atom because of the force of attraction to the nucleus. Take for instance, the distance from the nucleus here, the distance from the nucleus, the distance from this nucleus that is positively charged to this place. This distance from the nucleus to this side, the distance to this nucleus to this end, the distance varies. The further you go away from the nucleus, the weaker the force of attraction. Therefore, these electrons here, the electrons outside here, can easily be loosed out, or they can easily go into covalent bond formation because of their energy level. This is the first energy level, the second energy level. And to remove electron from here, it is easier because it requires less energy. The ionization energy, that's any energy required to remove 1 mole of electron from this shell, is lower than the energy required to remove electron here. The same thing goes. The energy required to remove electron here will be lower than the energy required to remove electron here. Why? The nucleus has an attractive force to these electrons. So the further you go away from the nucleus, the easier it is for the electron to be removed. Therefore, we come to what we call electronic configuration. These electrons, they have a pattern in which they are arranged. This is how the atom came into this, Rutherford came to this. These electrons are arranged according to their shells. We said 2n, 2 times n squared. That's how electrons are arranged. The first shell n, the first shell L equals to 2, which the first shell K, which is equals to 1, has how many electrons? It will definitely have only 2 electrons because it is 2 times 1 times 2, which gives only 2 electrons. And that is the first shell that is closer to the nucleus. And the force of attraction between those electrons, and the force of attraction between these electrons here and the nucleus is too strong. The second shell is L equals to N, which is equal to the second shell L, at the energy level L is 8. That is 2 times, if the shell number is 2, If the shell number is 2, we multiply this 2 times 2. We multiply it with 2, it is 2 square. Put in bracket 2 square. 2 square is 4. 4 times 2, it gives a total of 8 electrons. That is the second shell that occupies that. Continuously, that's how electrons are arranged. And they came to a conclusion that electrons are arranged in this form. The first shell must be 2. The second shell must be 8. The third shell must be 8. And 18 and above. That is how electrons are arranged in electron. That is the arrangement of electrons in an atom. Atoms of carbon, for instance, carbon has how many electrons? We go back to the periodic table, the sample periodic table. Carbon is of group 4 of the element of the periodic table. It has atomic number of 6 and a mass number of 12. Therefore, carbon has 6 electrons. And these 6 electrons, it shows that carbon has 6 protons. And it also has 6 neutrons right at the nucleus. This is carbon here. This is how it is represented. At the nucleus, we have 6 protons, we have 6 nitrogen, and then 6 protons, 6 neutrons. Then at the outermost shell, we have only how many electrons? There are 4 electrons that are revolving. We call them the valence electron. And these make carbon to form bonds with 4 different atoms from hydrogen, or any other compound that can donate 1 electron for sharing. Okay. Chlorine again, these are atoms of the same element. This is how atoms are represented. With carbon, we have 2 electrons. The first shell is 2. Then the last shell, the outermost shell, has 4. With chlorine, the first shell from this formula is 2, 8, 7. Chlorine is supposed to be 2, 8, 7. Now, since it has 17 protons, it has 17 neutrons. Therefore, the first shell is supposed to be 2 electrons. Then the second shell is supposed to be 8. Then the third shell is supposed to be 7 electrons. And this is how the electrons are represented in a configuration manner. 2, the first shell, which is equals to 2. The second shell, which is equals to 8. And the valence shell with 7 valence electrons. This is how these are represented in an atom. When we have all these, we can now come to how these atoms can react among themselves or with other elements to form molecules. And that takes us to the topic, the molecule. What is a molecule? What is a molecule? And now take us further to what is a molecule. Now, as I said, what is a molecule? A molecule is any substance. A molecule is a combination of atoms of the same element or different elements. Atoms of the same element can come together to form a molecule. Atoms of different elements can as well come together to form a molecule. Take for instance, here is chlorine. Take for instance, chlorine, which is a diatomic molecule. Take for example chlorine. Excuse me for some time. Take for example chlorine. This is chlorine, which is a diatomic molecule. Atoms, we say, atoms of the same element can come together and form what we call a molecule. Atoms of different elements can come together and form what we call a molecule. Therefore, in this case, take for example chlorine. This chlorine atom, this is a chlorine atom, which is here. Chlorine atom from the periodic table, chlorine has an atomic number of, from the periodic table, sample periodic table, chlorine has an atomic number of chlorine. It's a group 7 element with atomic number of 7. It has 17 protons. 17 neutrons, and how many? 17 electrons. If we arrange these electrons, we will have the first shell, which is n equals to 1, will have how many electrons? We have 2 electrons. N equals to 2, we'll definitely have 8 electrons, making a total of what? 10 electrons. Then N equals to 3. We'll definitely have what? So there are 17 electrons and we already have 10. What will now be left? 7 electrons, making a total of 17 electrons. So these 7 electrons are the electrons that are found in the valence shell. We call them the valence electrons. These are the valence electrons that are going to take part in a chemical reaction. These are the valence electrons that are going to be used in bond formation. Thank you. Now, this is chlorine. This is chlorine. Chlorine has 7 valence electrons in the outermost shell. It's chlorine. We have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, and 7. That's a chlorine atom. Atom of chlorine. It's an atom plus another atom of chlorine. It has the same 7 electrons. It's an atom of chlorine which will represent it in a dot form. 1, 2, 3, 4, 5, 6. These are the atom. These are the electrons in their outermost shell. These are the valence electron. If these two chlorine atoms they come together, these are atoms of the same element. If they come together, they are going to form what we call a molecule of chlorine, and it's going to be like this, represented like this: chlorine, chlorine, with 1, 2, 3, 4, 5, 6. This one donates 1 electron for the sharing. This is it. This other one, 1, 2, 3, 4, 5, 6. It has another 1 electron that has to donate for the sharing. Now, if you look at this one atom of chlorine, we have 1, 2, 3, 4, 5, 6, 7, 8. The octet is full and it is stable. We go to this other one, 1, 2, 3, 4, 5, 6, 7, 8. The octet is full and it is also stable. This therefore is this chlorine plus chlorine. That gives a chlorine molecule. That is how molecules are being formed. Atoms of the same element. Now, what are the conditions for the formation of such a bond? This is a covalent bonding. And what is covalent bonding for the formation of molecules? Covalent bonding is a type of bond involving the sharing of electrons, where the two partners they come together. This is one partner and this is another partner. They come together, and for them to have a stable octet of electron, they need to contribute 1 electron for sharing. I will give 1. These two can come together. This atom, these are the 2 atoms. This atom of chlorine and this atom, they come together. This atom donates 1 electron, and this other donates this other electron. This one here is represented by a blue, and this other one is represented by a black. And when they donate the 2, this is how a bond is formed between the 2 atoms of chlorine, making a molecule of chlorine. That is how it is being represented. This is how atoms are being formed in covalent bonding. The first condition for a covalent bonding to take place is that they must have valence electrons. They must have valence electrons. These are the conditions that enable for the formation of covalent bonding. There must be sharing of electrons. There must be sharing of electrons for them. The same thing, this is chlorine. And I can be represented in this form. Chlorine, to make with these 2 chlorine atoms, the chlorine, the sharing electron, and to form a stable chlorine molecule. This is how it is represented. Another example is that of hydrogen atom of the same element, hydrogen. Hydrogen of the periodic table, the sample periodic table, is a sample periodic table. Hydrogen of the periodic table is in group 1. It has 1 proton. Hydrogen has 1 proton and 1 neutron. Hydrogen has 1 proton and 1 neutron. In this case, hydrogen has just 1 electron in the outermost shell, and in order for it to be stable, the first shell must have at least 2. From this formula that we said, 2n square. Now the first shell is just 1. How many electrons are supposed to be there? We put 1 here, 2, 1 square. 1 square is just 1 times 2. There are 2 electrons there. But hydrogen has only 1. So hydrogen need another atom of hydrogen that they can come together and donate the electron so that each of them will have 2 and the other one will also have 2. And this is how the pairing is being done. This one donates 1 and this other one donates 1 and will be now a molecule and they are sharing here. If we will be sharing here, this one hydrogen will have 1, 2. It makes hydrogen stable. The other hydrogen atom we have 1, 2. They also make the hydrogen atom stable and now give the molecule of hydrogen stability. That is how it is. This is the stability comes about. Let's go to the second section we call molecules. Molecule formation and molecule formation, the shapes of molecules and how their bond angle are determined by the pairs of electrons. In this section, these are molecules we are through with atoms of the same element like chlorine and hydrogen. Let's go to the second section of it. Covalent bonding, shapes and bond angles. What are the steps involved in the formation of covalent bonding? In covalent bonding, we said all electrons must donate at least 1 or 2 electrons for all atoms must donate at least 1 electron for the sharing. Some can give 2, like in coordinate bonding, but the simple molecule we are dealing with, at least 1 electron is donated for the sharing. Now, a good example of this is of covalent bonding. Yes, this. Covalent bonding. In covalent bonding and how they determine the structure of it. Okay, now covalent bonding. Yes, take for instance, these are structures in covalent bonding and how they determine the structure and how the atoms determine the angle of the bond angles. We are given examples of chlorine atom, examples of covalent bonding. The 2 examples are beryllium fluoride, there is boron trichloride, there is ammonia, there is water, and there is methane. These are atoms of different elements coming together. And the policy for covalent bonding is for elements that are more than 2. For elements that are more than 2, the first thing you must identify the central element. Take for instance this. For this one, there are more than 2 atoms that are involved. There are more than 2 atoms that are involved here. Be, this. There are more than 2 elements that are involved. Beryllium fluoride, F2. There are more than 2 atoms that are involved. 2 atoms of fluorine and 1 atom of beryllium. What do we do? The first policy or the guideline in the formation of this covalent bond is you must identify the central element. After identifying the central element, the next thing is you must identify the valence electrons in these elements. The valence electron, because these are the elements that are going to be involved in covalent bonding. And the third stage is you have to arrange the covalent bonding, the valence electron, so that each atom has at least 8 electrons. Take for instance beryllium fluoride. Now there are two atoms of beryllium, fluorine, and 1 atom of beryllium. So we must identify the central atom, and the central atom is beryllium. This is the central atom, beryllium. The central atom, this is beryllium. 1 atom of beryllium, one atom of beryllium, and plus 2 atoms of fluorine. Now, there are 2 atoms of fluorine. This is beryllium that is here, the central atom, and it has 2 valence electrons. These are the valence electrons here. These are the valence electrons. Now, there are other 2 atoms, fluorine. As I said, fluorine. How do we know how fluorine is going to bond? In order for you to know the number of electrons that are going to take part in this bonding, in this covalent bonding, you have to go to your periodic table and look the position of fluorine there. Fluorine here is a group 7 element. Fluorine has is a group 7 element with 9 protons, 9 neutrons, and 9 electrons. And if there are 9 electrons, the first share of fluorine, if there are 9 electrons of fluorine, then the first shell should be 2. The second shell, the first shell should be 2. Then the second shell is supposed to be 8. But 9 take away 2. How many electrons are left? 7. So the first shell of fluorine is supposed to be 2, and the second shell is supposed to be 7. So there are 7 valence electrons in fluorine that are supposed to take part in this chemical reaction. So therefore, fluorine is here. We have to bond here and here. This is fluorine. These are the electrons. 1, 2, 3, 4, 5, 6, and this is electron that fluorine is donating for the sharing. We have here 1, 2, 3, 4, 5, 6, and this is the electron that fluorine is donating. It's always donating. That gives fluorine a linear structure, which is F, B, E, F, and this gives it a linear structure. This is how it is represented here. This is fluorine here. This is 1 atom of beryllium that is here, plus 2 atoms of fluorine, and there are 2 valence electrons. Just as I've explained here, there are 2 valence electrons. This one in beryllium, and there are 2 atoms of fluorine that are involved in this thing. Now, what do we do? The central atom is beryllium. This is beryllium here, and the central atom with 2 valence electrons. Fluorine now comes in with the 7 electrons. Has to donate 1. This is the donation that is doing here. This is the donation that is doing here. Then the other one will also donate its own here. Now, if you count the total number of electrons for fluorine, fluorine has 8, and this other side has 8. Now, this gives a straight structure for the bonding, and as chemists they put it, we call it a linear shape. It's called a linear shape with a bond angle of 180 degrees. That is how beryllium is supposed to be. Now, if you want to go into another compound, another molecule, formation of another molecule called boron trichloride. This is boron trichloride, BCl3. It's the same thing. There are 4 atoms that are involved here. Initially, the other one was 3, but now we have gone to 4 atoms that are involved. 1 atom of boron and the 3 atoms of chlorine. And as I told you from the map, always refer to your periodic table. Always refer to your periodic table. Those ideas may not come. The boron is of this is boron. It has 5. It has 5 protons, 5 neutrons, and 5 electrons from the atomic number. Which the proton that gives the atomic number, this is 5. This boron. I belong to group 3 of the periodic table. So this is 5. And if it is 5, how do we know the second stage is determination of the valence electron? From our formula that we said, 2n squared. Now, for the periodic table. Now the first shell of boron is supposed to, the first shell is supposed to be 1. So it is 1 squared, which is 2 electrons. Now there are 5 electrons involved. So 5 take away 2. The last valence electron of boron are supposed to be 3. So boron has 3 valence electrons, which is 2, 3. These are the 3 electrons of boron that are going to be involved in the sharing of electrons. So boron now, we have boron here, one atom, and the chlorine, 3 atoms, and 3 atoms. The central element is supposed to be boron. The central element is supposed to be boron, and boron must be attached to how many atoms of chlorine? They are supposed to be 1, boron, 2, and 3, because boron has 3 valence electrons. So this is boron here, donating one atom. That is boron there, donating one. Boron is also donating one here. Boron is also donating one here. It's chlorine, it's chlorine, it's chlorine. Again, how many atoms do chlorine have? How many electrons are in chlorine that are going to take part? We call them valence electron. We don't know the valence electron of chlorine. So the next thing, you refer to your periodic table and look the position of chlorine. This is chlorine here. This is chlorine here. Chlorine has 17. The atomic number of chlorine is 17. This 17 shows that there are 17 protons, there are 17 neutrons, and at the same time there are 17 electrons that are revolving around the orbit of chlorine atom. Therefore, these 17 electrons, these are the electrons that chlorine is having. And how do we know the valence one? The first share of chlorine from is supposed to be 2. The second share of chlorine is supposed to be 8, make a total of 10. Then the last share will definitely, so it is 17. 17 take away 10 will be, the last share will be 7. So chlorine now have 7 valence electrons that must participate in the sharing of electron. So this is chlorine here. 1, 2, 3, 4, 5, 6, and this one that it donates. Again, 1, 2, 3, 4, 5, 6, and this one that it donates. Again, 1, 2, 3, 4, 5, 6, with this other one that it donates. They give chlorine this structure. This structure, boron, this structure. Boron to chlorine, chlorine, and a chlorine. And this bond angle will definitely be 120 degrees. You see how these atoms are being arranged. Schematically, this is how the structure is being drawn. This is the boron atom. There are 2 atoms, 1 atom of boron, 3 atoms of chlorine. Boron has 3 valence electrons. Chlorine has 7 valence electrons. When they combine together, these boron plus 3 atoms of chlorine in the sharing of electrons, each and every one of the atoms is donating 1 electron for the pairing. Chlorine is donating here, is donating another one here, and is donating here to the central atom. And they give boron trifluoride a trigonal planar shape with a bond angle of 120 degrees as represented here. That is how it is. The next one is ammonia. This is ammonia. Ammonia. We have ammonia here. This is ammonia. Ammonia has 1 atom of hydrogen, 1 atom of hydrogen, and 3 atoms of nitrogen. But how do we know which is the central atom? Since there are 3 atoms here, and the ammonia is only, ammonia becomes the central. Nitrogen becomes the central atom. But you can ask yourself, if nitrogen is the central atom, how many valence electrons do hydrogen have? The next thing is, I will always ask you, you refer back to your periodic table. Nitrogen here is in group 5 of the periodic table. This is nitrogen. It has atomic number of 7 and a mass number of 14. This atomic number of 7 signifies that nitrogen has 7 proton, 7 neutron, and 7 electrons. That is nitrogen for you. Welcome back. So as we ended with nitrogen as a molecule in covalent bonding, we were at the stage of identifying the central element for ammonia. We were trying to identify the central element, and we said in this covalent bonding there are 3 stages. You identify the central atom. So there are 4 atoms here, 3 atoms of hydrogen and 1 atom of nitrogen. The central atom will definitely be nitrogen. And the other atoms that will be participating in the union, in the covalent bonding, will be the other 3 atoms of hydrogen. But the thing is this, you can always ask yourself, which are the electrons the valence electrons that are going to take part in the chemical, in the bonding? I've always referred you to the periodic table. Take nitrogen is here. This is nitrogen of the group 5 of group 5 of the periodic table. Nitrogen has 7 protons, 7 neutrons, and 7 electrons. And hydrogen has just 1. Therefore, so nitrogen has 7 in this case. It has 7 electrons. Which of these 7 electrons are the valence electrons? From the from electronic configuration, we said the first shell from the formula, the first shell was 2n, 2n squared. The first shell of nitrogen is supposed to have, this is 2, 1, which is equal to 2 electrons. Then the second shell 1, shell 2. The second shell will be 2. It's supposed to be 2. It's supposed to be 2, which is equal to which is supposed to be 8. But that's not the thing. The atomic number of nitrogen, the number of electrons there, atomic number, which is the number of protons, and which equals to the number of electrons, is 7. So we already have the first shell is 2 for nitrogen. Then 7 minus 2 is 5. So these are the only 5 electrons of nitrogen that are going to be involved in the covalent bonding. Now these 5 electrons, how are they going to be represented? Hydrogen, this is nitrogen here. This is nitrogen here. Nitrogen has 7 electrons. There are 5 electrons. The first 2 electrons, the other 3 valence electron, this one, this other one, this other one. This is 1 atom of nitrogen. There are 3 atoms of hydrogen involved. In trying to bond themselves, the central atom of this will definitely be, this is the nitrogen. The central atom from where it was here, when they react together, the central atom will have what? They bring all these electrons here. These are the 2 lone electrons of nitrogen. 1 electron of nitrogen, the other one, and this other one that are going to involve in sharing. Then there are other 3 atoms of hydrogen. This is there are 3 atoms of hydrogen, and they have only 1 valence electron. In this union, nitrogen will have to contribute these to the bonding. Nitrogen will have to contribute 1 again for the bonding, and the other and the last atom of nitrogen will have to contribute. And if you go round the first, take for one atom of nitrogen, 1, 2, the one that he contributed and the one that also nitrogen also contributed, makes hydrogen stable with 2 electrons in the first shell. This hydrogen is stable. This hydrogen is stable. Let's see whether the nitrogen itself is stable. Nitrogen had just 2, just 5, but 3 came from 3 atoms of hydrogen, making a total of 1, 2, 3, 4, 5, 6, 7, 8. A total of 8 electrons. That gives nitrogen a stable state. Now, this is the structure. This is the structure. Nitrogen, this nitrogen, hydrogen. This is the structure with this lone pair of electron here. We give nitrogen, this bonding here, bonding here. That give hydrogen, this lone pair of electron here. This is an electron-rich center. This electron-rich center, electrons are positively, and negatively charged. As we said, these 2 electrons will always repel each other. There's a repulsion. So there is an effect of these electrons, the lone pair of electrons, on these other bonded electrons here. There's one donated by hydrogen, and there's also one donated by chlorine. Nitrogen, and there's also one donated by hydrogen. These are electrons here. This bond also represents a pair of electrons. This other bond also represents a pair of electrons. But there is that effect, the repulsion between the lone pair of electrons and this bonded electron. So this repulsion, it helps to do what? It pushes this electron, these bonded electrons. This force from here, from the lone pair, help to push this, and the atom, the bond angle will now be like this again. Hydrogen, again here, hydrogen. See, trying to give hydrogen like some sort of a pyramid. It gives some sort of a pyramid. Now, this gives hydrogen this structure here, a trigonal pyramidal shape. And as it is pushing this one, as it is pushing this bond, the bond comes closer here. It pushes this one, the bond will now come but this way. As this one is pushing this one is not coming this way. That's why you see it like this, coming like that. As each of these, the lone pair is pushing this bonded pair of electron. The bonded pair of electron is also pushing this other bonded pair here. As they are going like that, the bond angle are becoming smaller and smaller, resulting in the bond angle between this bond and here to be 107 degrees. This lone pair of electrons has a big impact in shaping the molecule and in determining the angle of the compound. That is how it is. The same thing goes with oxygen, with water. Let me show you something here with water. For water, this is the same thing. This is the same thing with water. A molecule of water here, this molecule of water. Water has what? Water has 2 atoms of oxygen, of hydrogen, and 1 atom of oxygen. This is 1 atom of oxygen. These are 2 atoms of hydrogen. Now, how many electrons are in oxygen? How many valence electrons are there? Again, I refer you back to the sample periodic table, which is not to scale. I am saying this hydrogen, this is oxygen. Oxygen belongs to which group of the periodic table? Oxygen is group 6 of the periodic table, and it has 8 proton, atomic number of 8, showing that it has 8 proton, 8 neutron, and 8 electrons. Now, this hydrogen, this oxygen like this, if there are 8 electrons there, the first shell of it has 2. Then the valence electrons are supposed to be 6. These are the 6 valence electrons that oxygen is having. These are the 6 valence electrons that oxygen is having. The first 2, the 2 electrons here, this other 2, and this last 2 electrons that will need something, that will need another atom with a single electron to bond with, which is hydrogen. Now, in trying to arrange the bond, this which is the central atom. The central atom here will definitely be oxygen because there are 3 atoms here. The 2 atoms of hydrogen and 1 atom. So the central atom is oxygen. We place the central atom here. This is the central atom here. Now, since the central atom has 2 lone pair of electrons, it's donating 1 electron. This is the 1 electron that is donating, and this other one. Then hydrogen now comes because hydrogen has only 1 electron in the atomose shell. So now, it now comes. It donates the 1 electron to have 2 electrons making it stable, and another one. This other hydrogen atom donates 1 to make it stable, and give this structure of water. This is the structure of water. But that's not how the structure of water is supposed to be, because there is definitely going to be an effect caused by the lone pair of electrons. It's not only 1 lone pair of electrons, but there are 2 lone pairs of electrons. This one and this one, which are represented here, this and that. What are the lone pair electrons going to do? They are going to exert a force on this bond here, the oxygen-hydrogen bond. They are going to exert a force. And that force is going to repel, is going to cause a repulsion among the electron, the bonded electron and the lone pair of electrons, pushing the bond angle together, pushing the angles to go closer. When it is bonded together like this oxygen, this is it, and this hydrogen. This is a lone pair of electron. This is a lone pair of electron. Now, this is going to push this. This is also going to push this one. This lone pair of electrons is going to be pushing this one, and this one is going to be pushing. And at the end of the day, you will see but hydrogen like this. The bond will be hydrogen, and like hydrogen, lone pair of electrons, their effect. Then reducing the bond angle. So it has pushed this angle here closer. It has also pushed this bond here, this oxygen-hydrogen bond closer, and this other one closer. I'm trying to give the bond angle to be like a V shape. And this gives hydrogen this type of shape. It is either a bend, we can call it a bend shape, or a V-shaped structure. So therefore, the bond angle for water is bend or V shape with a bond angle of what? With a bond angle of 104.5 degrees. The effect caused by the lone pairs of electrons that exert a repulsion on the bonded pairs. The last example on this is methane. Methane is, carbon has how many electrons in the atomic shell? Methane is this compound of methane, CH4. We have one atom of, we have one atom of. Welcome back. We're on methane. We are concluding on methane. There are 4 atoms of carbon, there are 4 atoms of hydrogen and 1 atom of carbon. Carbon has 4 valence electrons and the hydrogen has only 1. This is carbon represented here as the central atom. Now it has 4 electrons that is going to, for valence electron for donating. Hydrogen will have to attach itself by donating 1 electron. This hydrogen attaches itself by donating 1 electron, it attaches itself by donating 1 electron, and this one attaches itself. It gives nitrogen this methane this structure. But the way the angles are arranged makes methane to have a tetrahedral shape. These are the bonds are being arranged. It gives methane a tetrahedral shape with a bond angle of 109.5 degrees. This is how atoms are arranged. Next time, we will continue with empirical formula and molecular formula. Thank you very much. I wish you a happy day. Thank you.